Okay, so let me start off by showing you web work, what's due this week. So if you look at it, let me just double check something. So the quiz is today after class. I'm going to show you that as well. So first, web work. So we're up to 2.6. That's my goal to finish up today. So 2.6, 2.3, 2.9, I modified these due dates. So now they're due on the 14th, which is this weekend, I believe. Yeah, so that's this Sunday. So make sure you start working on 2.6 after we finish today's lecture. And then we're going to take a quiz after class. So let me show you where you will find the quiz. So if you go back to your Blackboard page, so it should look like this before joining Collaborate. And on the left side where you have course materials component, if you click on it, you'll see the quiz. Not now. So right now it's closed for you guys. I can see it because I created the quiz, right? Funny. But once I hit 7:38, 7:37, you will see the quiz pop off on your screen, this page, okay? So you have to manually go back to this page, click on course materials. You should see quiz 1. Now, another thing you have to keep in mind, be very careful when you enter your answer. It's a multiple choice quiz. So you'll see one question at a time, just like the pre-quiz you took. Do the work on a scrap paper and then choose the right answer. Be very careful how you input the answer, because I'm not going back to give you partial credits because it's a quiz. There's no partial credit for a quiz. But for exam, I will go back to your work and give you partial credits. So I mentioned that first day of class, second day of class. Hopefully you guys are okay with that. Any questions on that? So there are 4 questions on the quiz. You have 20 minutes, so 7:38 all the way to 8 o'clock, something like that. So, but it shouldn't take you 20 minutes. If you've been doing the homework, if you've been doing recommended question from the text, you should finish within 10 minutes, first 10 minutes of the quiz. So you don't need to send me your scrap work. That's just for exams, okay? This one, you just do it on Blackboard, carefully submit your answers, and you're good to go, okay? So that will take place today at 7:38 p.m. So I'll stop the lecture around 7:35 and we can chat a little and then you can start the quiz. So I will be here on Collaborate open just in case anyone has any trouble or if you run into an issue. So that way you wouldn't miss me because I will be here with you as well, okay? Any other questions? Are we good to start? Yeah. Okay. So again, if you want to talk through your audio, all of you are welcome to do so. So I'm going to go ahead and start writing on my OneNote for today's lesson. Today we're going to do more exciting things. I'm going to do 2.6 and I hope you guys will enjoy it as well. So before I start, I do want to give you some recap on what we have done so far and just to keep you up to date what's coming up. So here's an update. So just everything I mentioned earlier, I'm just going to write it on my OneNote just in case you want to look back and revisit. So here are the updates for today. So one, so web work. So start working on, so start with 2.6, 2.3, and so on. So these are due this weekend, so you can start whenever you're able to. So maybe tomorrow, maybe tonight, whenever you're able to start working on them. So that's this week. The second update is we have a quiz 1 today at, let's just call it 7:38 p.m., right? Sorry, broken time, but you know what I mean. 7:40 is when we officially finish, but 7:38, I think it'll be available to you on your course materials section. And the third update I have is office hours. So I'm going to hold longer office hours. So instead of 5:30 to 6 on Tuesdays, so my updated office hours is going to be 5 p.m. to 6 p.m. So right before class on Tuesdays. And I'm also holding office hours on Thursdays. Uh, so I do want to do after class, but then it's really late. So I don't know if all of you are available to come. Is 8 to 9 p.m. too late for you guys? What do you guys say? Okay, so Liana is fine with that. Um, okay, so I'm gonna keep it. What about rest of you? So you guys are very quiet. I can't assume if it's okay or not. So Tuesday 5 to 6, I think it's okay, manageable, right? So I want to hold another office hours, but let me know if someone has trouble with both of the office hours. So Alex is good, Sadia is good. Okay, Jay is good. Okay, edit. So I'm just gonna keep it for 8 to 9 p.m. So that'll be after class, right? We can start at like 7:45 if everyone's okay with that too. Uh, so Thursday will be after class, Tuesday will be before class. Uh, if you need a different timing, then send me an email. I'm more than happy to come out and help you another timing. So for now, officially, those are my office hours, okay? All right, so having said that, that's the update. And now let me give you a recap on what we have done so far. Right. So far, we are working on solving first order differential equations, right? So we're solving first order differential equations. So we have discovered the first method. It was separable. If the equation is separable, then you use the separation of variables to solve that particular equation. And the second method we talked about was homogeneous. If the given differential equation can be written as a function of y over x, then the given equation is considered to be homogeneous. And then we spoke about how to approach from there. And then we talked about linear first order. So for linear, we have to use an integrating factor. So we came up with this formula for integrating factor, which we have mu of t as e to the integral of p of t dt. And you fill in the rest, right? That's the magical integrating factor. I showed it to you how to derive it, just in case if you forget on a test or a quiz, you can always derive it, right? So that's that. And now today we're going to talk about the last method, which is the fourth method to solve first order. And that's going to be our focus for section 2.6. And then after that, we're going to go back to applications to first order. That'll be section 2.3. So first, my goal is to just finish up all the methods, and then we'll do application. Okay, so continuing to 2.6. Any questions so far? Okay, I'm assuming that's a no. Again, please let me know if you guys have any questions. So 2.6, we're going to study exact differential equations. Okay. So before I show you how to use the method, let me give you some background and just show you where things are coming from a little bit. Okay. So suppose we want to solve the following differential equation. So let's solve the differential equation so say we have 2xy, no, let me, 2x plus y squared plus 2xy y prime equals 0. So suppose you're given this differential equation. So first thing you want to do is just run down the methods and see which one is applicable to find solution to this differential equation. So if you look at it, is this separable? Because that's the first method we study, right? Is it separable? What do you guys think? Okay, Jay said no. Okay, good. So it's not separable because there's no way we can sort of isolate y and x and with its derivative, right? So it's not separable. That doesn't work. Now, is it homogeneous? Right? Can it be homogeneous? Well, you can check, right? You can check by doing the following substitution. You can do you can substitute x with k times x and substitute y with k times y and then fill in the blank, right? So you can go through the procedure and check if it's homogeneous. So for now, I'm going to say no because my purpose is to explain you how to use the exact method. Now, next thing is it linear? Is this equation linear? So we're kind of holding on to this homogeneous part. You can verify that. If it is, then you can use that method. So is it linear? No. So it's not linear. So we see it's not separable. It's not linear. So we can go ahead and find another suitable method to solve this differential equation. Okay, so that's what we're seeking. So let's find a suitable method to solve this differential equation. Okay, so that's the goal. So what I'm going to do, I'm going to take the given equation and I'm going to rewrite it this way. So we have 2x y squared plus 2xy. So instead of writing y prime, I'm going to write dy dx equals to 0. So just rewriting. Now what I'm going to do, I'm going to multiply both sides by dx so I can isolate my partial derivatives, right? So we have 2x plus y squared times dx plus 2xy dy equals to 0. Okay, so we have a function in front of dx and a function in front of dy. So now here's the thing you want to notice. I'm telling you that this magical function, so observe that this function, let's call it phi of xy equals x squared plus xy squared solves the equation above. Okay, so observe that this function is a solution to the differential equation that I gave it to you. Now, why, right? How did I come up with this magical equation? So that's like the big question. Where is this equation coming from? So before I show you where this is coming from, I'm just going to kind of do a back check where I'm going to take the partial derivatives of this equation and show you it is what's given to us previously. Okay, so here's something you want to just observe. So if I take phi and I take its partial with respect to x, what do I have? So if I take the partial derivative with respect to x, we have 2x plus partial derivative of x y squared with respect to x, it's just y squared. Okay, now what if I take this magical function phi and take its partial with respect to y? What do I get? I get 2xy. So what do you notice? What do you notice from these partial derivatives and the differential equation I gave you? So, right, so they appear in your original equation, right? They're the same. So that's what I'm saying. So if you look at it, so here's my partial that I just computed respect to x, and here is my second partial that we computed respect to y. So that means this function is a solution to this differential equation because you have partial derivatives along with some function of x and y. So we're going to introduce some different notation to simplify things. So what I'm going to do, I'm going to call this partial m of xy, just a different notation. And I'm going to call this partial n of xy, or you can just call it m and n. Okay, so we're just giving everything a name. Now, how do we know this equation was exact equation? So here I'm going to give you a theorem from Calculus 3. If you have forgotten it, this is the time to recall. Do you guys remember Clairaut's theorem? I think that's how you spell his name. So this is from, I think, Calculus 3 or 2, whichever calculus you saw it. So it involves partial derivative. Okay, so Jay said no, that's totally fine, right? We usually don't remember a lot of theorems from calculus, but once you hear them, then you kind of recall, oh, I remember that, right? So maybe you'll have that expression. So Clairaut theorems, I don't remember the full formal statement, but I'll just put it in my own words. It says if the mixed partials, say f of xy, right, and f of yx, these are the mixed partials, are continuous, and a region, you can always talk about more detail, but we just want to get to the idea. Then we can say that mixed partials are always equal. So that's sort of like the shortcut version of Clairaut's theorem, that when you take the partial derivative of x respect to y, and when you take the partial derivative of y respect to x, the mixed partials are always equal. So what do we notice here? If you go back to this differential equation I gave you, I have my first derivative respect to x, phi of x, right? And then I have my second partial respect to y. Now we want to say that if I take the second partial derivatives, if those two partials are equal, then the given differential equation is exact. So that's the idea we're going to apply from Clairaut's theorem, that if we take the second partial derivatives for these first partial, and if they're equal, then we said that the equation is exact. So we want to show this statement holds. Okay, so let's check it out. So I'm going to take phi of x, that was the first partial respect to x. I'm going to differentiate it now respect to y, okay, because that will be the mixed partial. So what is p xy? So you look at phi of x, which is 2x plus y squared. Now I'm going to differentiate this respect to y. We get 2y. So that's the second partial respect to y. And now I'm going to take phi of y, but now I'm going to differentiate it respect to x because I want the second mix partials. And what is that going to give us? So if I take phi y and differentiate it respect to x, I get 2y. So what do you say? They're equal, right? They're equal. So therefore, we can say that the original equation, which was given to us, is exact. So that's what it means for an equation to be exact. When the mixed partials are equal, we say that the differential equation is exact. So that's something you have to know. So once you know it is exact, now we use the method of exact to find solution, meaning find this magical function phi. Well, in this case, I give it to you, but you're not going to be given, or it won't be so easy to determine just by making observation. Okay, we have to come up with technique to find this function phi. So now the question is, how to find this function phi of xy, which is the solution to the differential equation, right? So let me give you a statement. So first, we need to check that it is exact. The equation. So if it is exact, then we can use this method. So first you want to check that the equation is exact. Okay, and how do we check that? I just showed you, you show that the mixed partials are equal, but I'm going to write it in more detail as we go along. But suppose we're given the following. So what are we given? We're given the differential equation in this form. So here we have this magical function, right? And we're calling this, what is that we're calling? M. This function is called m of xy. And this function right here, we rename it, this was partial y, we name it as n of xy. So if you're given the following differential equation, okay, so if you're given xy times partial x, right, plus n of xy partial y equals to 0, if you're given this statement, and there is a function phi of xy such that the partial derivative, so phi of x, which we call it m, and phi of y, which we label it as n, so and assume we have continuous partial derivatives. Okay. Okay, so if you're given this differential equation where m represents your partial x and n represents your partial y, then we're going to make the following statement. So the equation mxy dx plus nxy dy equals to 0 is exact, right? If and only if m, so you take m and you take the partial derivative respect to y. If you look at it, that's what we did here. So we took m, we took its partial derivative respect to y, and then we took n, its partial derivative respect to x, right? Those were the mixed partials. So if you do that, so my and then you take function n, take its partial derivative with respect to x. So if and only if these two mixed partials are equal, then we said that the differential equation is exact. Okay, so the equation is exact if and only if my is equal to nx. So that's the final statement. Okay, so any questions up to here? Now, before I show you the method, let me give you another background. So what is this function phi? So again, I'm going back to this example we have written. We had m as 2x plus y squared and n as 2x. So we have the following statement. So coming from above, so we had m, which was 2x plus y, and then we had n, which was 2xy, right? So we had this equation. We had 2x plus y dx plus 2xy dy equals to 0.
Professor, m was 2x plus y squared.
2x plus y squared. Yep, thank you. So 2x plus y squared, and then n is 2xy. All right. So we had that initially, right? And then we relabeled that m and n. So what do we really have? We have phi of x dx plus phi of y dy equals to 0, right? So that was the kind of like the back step. We had the partial respect to x, partial respect to y equals to 0. But if you recall, what does that really represent? Well, that really the derivative respect to x of the function phi of xy equals to 0, right? So this is sort of like chain rule from Calc 3. So if you were to differentiate this function phi respect to x, you have the step above. Now, if I want this function phi, well, I need to integrate both sides. So we're going to go ahead and integrate both sides. So if we integrate both sides, we have, right, integral of 0. That looks silly. But phi of x, well, when you integrate 0, what do you get? Or if you integrate 0 is like a constant, right? So, well, think of a 0 as a constant, right? So if you take any constant and you differentiate, what do you get?
So you get the letter with respect.
Right, c, right? Just a
Yeah, C.
constant. Exactly. So what is this function phi? Well, this function phi is nothing other than just a constant. So what do we say? So we say that the solution, so we have the solution. So we have phi of xy is equal to, what was the solution? So it was x squared plus xy squared, x squared plus xy squared. Well, what is phi? We just discovered phi is nothing other than just a constant. So we can say this is c is equal to x squared plus xy squared. So that's the solution to this differential equation, right? But now let's use the method to find this function. So now I'm going to show you what is the method. So here is how we're going to compute phi. Right, so let's compute it by showing steps. So what I'm going to do, again, I'm going to go back to this differential equation right here. So the method goes as follows. You look at one of your function, either m or n. So I'm going to go ahead and take just m, which is 2x plus y squared. So you take the function m, which is 2x plus y squared, and we're going to integrate. So we integrate m, but you're going to integrate this respect to x. So we have the integral of 2x plus y squared back to x. So if you integrate, you get x squared plus, if I integrate y squared, well, I get xy squared because y is a constant. But plus of constant, but instead of putting a constant, we're going to put a function of g, of y. Okay, a function of y. And this is where we're calling the function phi of xy. And then at the end, we're going to call phi is just a constant. But now the goal is you want to solve for where is this function g. So we want to solve for this function. So what are we going to do? We're going to take phi and differentiate respect to y, so that when you differentiate g of y, you don't get 0. So we're going to take phi and differentiate respect to y. So we have, if I differentiate x squared respect to y, that's 0. If I differentiate xy squared respect to y, we get 2xy plus, now if I differentiate g, that will be g prime of y. Now what is phi of y? Well, isn't phi of y the other part? Phi of y was just 2xy, right? So if you look at it again, right here. So phi of y is just 2xy, because that's what we're calling the function n. So this is equal to n of xy, which is 2xy. Well, our goal is to solve for this function g prime of y. So I'm going to go ahead and subtract 2xy. So then we have the following. G prime of y is equal to 0. Well, then what is g then? How do we get g from here?
You integrate on both sides.
All right, so if we integrate, we get c. So this function g that we just computed, it's nothing other than a constant. So our solution, therefore, is phi of xy is equal to x squared plus 2 xy squared plus a constant c. But what did we discover about phi? What is this function phi?
It's also a constant.
Right, so that's also a constant. So therefore we can say, so you have a constant and then you have another constant on the right side. I can just put them both together and say they're just equal to a constant. So we can say that x squared plus xy squared is equal to just a constant. Now, is that the solution we got initially when I say observe? Let's check. So if you go back to my observation, so right here, phi, this magical function that I said solves the differential equation, is x squared plus xy squared. So there you have it. You have the steps. How do you compute this function phi? Now you could have gotten this solution by choosing to integrate not m, but you could have chose to integrate n and then do the same thing. You compute phi of x instead of phi of y. Okay, so those are the steps for solving an exact equation. So any questions so far?
How did you get g of y on the top from the
So
integration?
right, so from here to here, I integrated respect to x, so I got x squared plus xy squared, and then plus a constant c, right? So instead of writing c, we're calling it a function of y, so call it g of y. Okay, now suppose you didn't pick m initially, you pick the function n to integrate. So you'll be integrating respect to y. So that means this g of y will now become g of x, because whatever you integrate respect to, your constant is a function of the different variable. Okay, so let me just write it in words. So in summary, and then I'll do a few more examples with you guys. So you can do exact method in two ways. So two ways to use method of exact. Okay, so one is, so you can pick and choose which one do you want to integrate first. Do you want to integrate m or do you want to integrate n? So if you choose, so choose which function to integrate first. Okay, so suppose, for this problem I chose to integrate m, right? So if you choose to integrate m respect to x, and you do the integration, but you have to tag in g of y. That will be the replacement for your constant c when you first integrate. And then to find this g of y, you would differentiate, right? So first thing you integrate, then you differentiate. So let me just use notation, it's easier. So then you differentiate respect to y to find g of y, and then you integrate respect to y, right? And then you integrate g prime of y respect to y. So I hope this makes sense, but again, I'm leaving out details because those are the details you will fill in depending on which problem you're working on. Now this step could change depending on if you pick n to be the function start with, or so you could have picked to integrate n, but that will be respect to y, right? Because you'll have n times dy. So if you do that, you will tag in the function g of x instead of g of y, because if you differentiate respect to x, you have to integrate respect to y. And then fill in the blank, okay? So now let me do another example to illustrate how this method really works. So here's another example. Let me know if you guys have questions. So let's solve the differential equation 2xy dx plus x squared minus 1 dy equals to 0. Okay. So I want to show that the mixed partials are equal. So the way for us to do that is to actually identify which one is m and which one is n. So which function is my m and which function is n? So 2xy is m, that's what J says. So this function is m, right? It's next to dx. Function is n because it's next to dy. So that's another way you can remember. So we want to check if I take m and its partial respect to y, is it equal to n its partial respect to x? Right? We want to see if this is true. So let's do that. So I take m, which is 2xy, and I'm going to take its partial respect to y. So if I take partial respect to y, I get 2x. Now let's take n and take its partial respect to x. We get 2x. So we see that the mixed partials are equal, right? So we can say that it is exact. Okay, so we have shown that the equation is exact. Now we can use the method of exact. Well, what does the method say? So the steps are, so they're not so clear because it's a lot of wording. I just put in a lot of symbols into it. So I can pick either m and then integrate respect to x, or I can pick n and integrate respect to y. So this time I'm gonna pick n, because the previous one I picked m. So I'm gonna go ahead and pick n and integrate respect to y. So my function phi that I am after, it's going to be the integral of n respect to y, so it'll be x squared minus 1 dy. Okay, so let's do that. So if I integrate, I get x squared y minus y plus, now what is the function we're going to tag in this time? So because we integrated respect to y, you're going to tag in a function of x. Okay, so I think you guys got it. Right, so yeah, all of you got it. Liana, Ingrid, and Anik. So we're going to tag in a function of g of x, because when you differentiate respect to x, you want to make sure it survives. It doesn't go to 0. So we want g of x. Okay, well now to find this g of x, we're going to have to differentiate phi that I'm calling respect to x. So we're going to take this function phi and differentiate respect to x. So what do we get? We get 2xy, derivative of y respect to x is 0. Derivative of g of x, that will be g prime of x. So see how it survived? It didn't go to 0, right? So that's the catch. Now what is phi of x? Well, phi of x is n of x, right? That's the new notation. Sorry, not n, m. That's 2x y. So this is equal to m of xy, which is 2xy. Well, now let's solve for g prime of x. So again, 2xy cancels out. So we have g prime of x is equal to 0. Well, now you integrate to find g. So g is nothing other than a constant. And now we go back to our solution. So here's the solution. This is going to be weird red. So the function that we're calling phi of x, it's going to be x squared y minus y plus g of x. Well, g is nothing other than a constant. And then we're also calling phi as a constant. So we have x y minus y is equal to a constant. So that would be the solution to this exact equation. So you're kind of like playing around with derivatives and integration. You integrate, you differentiate, and then you differentiate, and then you integrate. So kind of like going back and forth. It's a nice jump, right? But it's fun. I think so. So Maharon, so G is not always 0. So somehow the examples I picked, G happens to be 0. Sorry. Yeah, I could have picked better examples. So yes, so you could have solved this equation by picking, so here I picked, which one did I pick? I picked n when I'm integrating, right? So here you could have picked, so go back. So I picked n. You could have picked m and just go along the way with dx and then tag in g of y, and then you would differentiate respect to y, and then you would integrate respect to y. So you just have to remember those steps. So you should still get the same answer if you picked m instead of n, okay? So any questions on exact equations? So phi is always a constant, right? So whatever solution you get, like right here, so phi is equal to x squared y minus y plus g of x. Whatever you get, you always equal to phi, and phi is just a constant, so we just equal it to a c, a constant c. So the final step is right here. You always let your answer equals to a constant. And then if I give you an initial condition, you'll solve it from here. Okay, so any other questions? Okay. Okay, so J, you got x squared y when you picked M. Okay. So let's do that. So let's do that on the side. So we should get the same answer, right? So you're missing y. Let's figure out why you're missing y. So what if, so I'm going to do this on the side. So what if we picked the other function to solve instead of n? So here's the second part. So what if, right? So say I'm going to find this function by integrating m instead of n, okay? So what is m? Well, m happens to be 2xy. So this is equal to 2xy dx. So if I integrate this respect to x, we get x squared y plus, now because you integrated respect to x, you're going to tag in a function of y, g of y, okay? And now I'm going to differentiate this respect to y, so I get phi partial y is equal to x squared plus g prime of y. Well, what is phi of y? Well, phi of y is nothing other than n, which is x squared minus 1. So that's x squared minus 1, right, from the original equation. And now your goal is to solve for g prime. So I'm going to subtract x squared from both sides. So we have g prime of y is equal to -1. Well, now we integrate both sides. So let me know if that makes sense. Oh, you got it. All right, so you get a -y coming out from here. So in this case, g is not a constant. It's actually a function of y. So now if I integrate respect to y, I get g of y is equal to -y because you integrated respect to y. Well, that's the function we're going to tag in right here. That goes right there. So what is our phi? Well, we said that phi of xy is equal to x squared y minus g. Well, g is y. And then what is phi? Well, phi is also a constant, right? So our final answer will just be x squared y minus y is equal to a constant. So even if you picked m to start with, you still get the same answer, right? Like right here. So I put a big equal sign. They're equal. So it doesn't matter which approach you start with, either m or n, as long as you follow the procedure of its variable respectively, then you should get the same answer at the end. Okay. Anik, do you have a question?
Yeah, so how do you know that the derivative of the function g of x is -1?
So I solved it right here. So if so let me show you. So I set these two equal because phi of y is n, right? It's n right here. This is phi of y. So n is phi of y and m is phi of x. Those are the new notation we adopted when we start talking about this method. So then here, looking at the yellow, phi of y, phi partial y is equal to x squared plus g prime equals x squared minus 1. And your goal is to solve for g of y. So I subtracted x squared on both sides. So I get g prime of y equals to -1. And then I integrate respect to y to find this function g of y. Okay. So you could put -y plus constant, Carolyn, but because phi is also a constant, it combines to just one constant, right? So even if I put another constant right here, right, that C gets eventually swallowed by phi, because phi is also a constant, right? You can kind of put them together, right? So that's why I kind of ignore writing plus C, but if you want to, yes, you can write it. All right, so are we good so far? All right, so let's do one more problem, okay? And then we'll move on to 2.3. So let's do another exact equation. Okay, let's try this one. So we want to solve the following. So let's, all right, so Sadia, you got it. Okay, yeah, okay, yeah. All right, so that's good. Let me do this problem. I think this is a nice one. So let's solve the following. Let's do 3, no, sorry, not 3. Y over x plus 6x plus ln of dx, ln of x minus 2 dy equals to 0, assume x is positive. So I'll give you a few seconds, just jot down what you think and how you would approach this question. Okay, so hopefully you had some seconds to think about this question mentally. So you know it's not linear and it's not separable, right? So yeah, I'm going back to the question. So we're gonna test if it's exact, okay? So I have a function tagged with dx. So I'm gonna go ahead and label that one m, right? So let's label this m of xy, and I'm gonna label this one n of xy because it's next to dy, right? So correctly identify your m and n. Now, if you also remember, n is the notation we use for partial y, and n, so somehow my question disappeared. Okay, got it. And n is the function we're calling phi of x, because we're going to come back to them when we solve along the way, okay? So again, there are a lot of notation flowing around. Just make sure you understand them. Now, I want to check if it's exact. So I'm going to take m, and I'm going to differentiate it respect to y. And then I'm going to take n, I'm going to differentiate it respect to x. And if these two partials are equal, then we're going to say the equation is exact, and we proceed with the method of exact. So I'll give you a few seconds. Take those derivatives quickly, right? Derivatives should be your best friends. You can do them very fast. Hopefully, if you can, just train yourself so that you can kind of do them mentally. Okay, so let's start. Hopefully you had a few seconds to derive them. So m partial y, so I'm going to take derivative respect to y for m. So that will give us, so the first term is just going to be 1 over x, and the second term is going to be 0 because 6x is behaving as a constant. Now what about n partial x? So I'm going to take the derivative of n respect to x. I get 1 over x. Derivative of 2 respect to x is constant. So hey, this is Fantastic, right? So, Eureka. Know what that means? No, okay. Um, it's it's kind of like a way of when you discover something and you feel joy, you say Eureka. I think it's in Greek. I'm not sure, but probably in Greek. Yeah, so Sadia, you got it. Is it Greek? Probably, right? Who knows? All right, so we see that the mixed partials are equal, so we have exact equation. Okay. All right, so we're going to proceed to the method of exact. So now I have choice. I can either pick m and integrate respect to x, or I can pick n and integrate respect to y. Now, what do you want to do? You want to be clever here. You don't want to just pick them and randomly and integrate them, because integration can be difficult sometimes, right? Now, I would say if I were to do this problem, I'm going to pick m to integrate, because if you want to integrate n, you're working with ln of x. How do you integrate ln of x?
Professor, could you change it to the exponential and then integrate the exponential and then take that answer and then go backwards again? Or would that be too convoluted?
No, I wouldn't change it to exponential. Yeah. So for this question, it's nice because if you take n and integrate respect to y, ln of x is just playing as a constant, right? It's not a big deal. But if you had ln of y and you're integrating respect to y, then how do you integrate ln of y? Right? So let me know if that makes sense. In general, if you're to integrate the function ln, which method do you use from integration technique to integrate that?
Is it integration by parts?
Exactly. So you're going to run into more work because you will be integrating ln by parts. So that's why sometimes it's okay to pick m if it's easier, and then if n is easier, then you pick that one. So be clever with your choice. That's the idea. Okay, so in this case it doesn't really matter because I think we can just go ahead and integrate because these are nice uh, mixed partials. So I'm going to go ahead and pick, doesn't matter, right? So let's pick m. So the function phi that we're after, it's going to be the integral of m dx. Well, what is our m in this case? We have y over x plus 6x, and we're integrating respect to x. Okay, so here again, y is playing as a constant, so the integral of 1 over x, that's just ln of x, plus the integral of 6x respect to x, it's going to be 3x squared plus what?
G of y.
Right, so we have to plug in g of y. And now we're going to take this function and differentiate respect to y. So that will give us partial phi of y. So we have ln of x plus second term is 0, and the last term would be g prime of y. Well, what is phi of y? Well, phi of y is n, right? So we have ln of x minus 2. And then here you see that the ln's will cancel out. So what we have is the function g prime of y is equal to negative 2. So what is g of y? What's the integral of -2 with respect to y?
Negative
Right.
2.
So this is going to, yep, correct. Absolutely. So this would be -2y. And again, if you want to add plus c, that's up to you, but we're going to call phi is c. So I'm going to reserve that for phi. So what is phi? Phi is going to be, so therefore, phi of xy is equal to y ln of x plus 3x squared plus g, well, g is -2y. And all of these, we're going to call it equal to a constant. So we have y ln of x plus 3x squared minus 2y is equal to a constant. And then after this, you can plug in your initial conditions if you have one. We don't have one, so we will finish it right here. So that will be our solution to this differential equation. Now, how can you check your answer? You can check your answer by taking its partial derivatives. And you'll see the partial derivatives will happen to be the original function. So where is it? That's right here. So if you get the initial equation as a partial derivative, then you'll have the right answer. But hopefully you did your integration and differentiation correct. So let's take this as an answer. So any questions for exact equation? So that's the method of exact. That's the last method we have. Okay, how do you guys like it? Okay, that's good. All right, so yeah, so that's exact. Pretty interesting, yeah. So these are the 4 methods you have to solve first order. Okay, so we went through all 4. Now, you should be able to do section 2.9 because the idea with 2.9 is just putting all different first order differential equations together and having you decide which method is applicable to the given equation. Okay, so you'll have to kind of go through the list. Is it separable? Is it linear? Is it exact? Is it so and so? You just keep going down the list. Okay. So yeah, yeah, it makes you go back to calculus 3. Bethany, to answer your question, I'm gonna say no because I haven't run into that kind of situation yet. If so, first thing you always want to do is if it's separable. So if the equation is not separable, if it's not linear, then you try to see if it's exact. If it's exact, you check, right? My is equal to nx, and then you use the method of exact. And if it's not separable, if it's not linear, you can also see if it's homogeneous. If it's homogeneous, then you use the substitution y over x. So none of them really overlap. So I would say no to your question now, unless I run into something that looks like, oh, probably, right? But yeah, they're very specific setup for each differential equations. So I would say 1 per equation. All right, so that's that. So now we're going to move on to applications. So going back to section 2.3, we're going to study application of first order. Okay, so we're going to have some fun, more fun. They're pretty nice. I like these applications. They're good. So I hope you'll enjoy it as well. So we're going to start with section 2.3 for the remaining time. So 2.3 is modeling first order. So you see that this section is labeled after 2.1 and 2.2. That means the equations that you're going to apply to model, it's going to be either linear, so you'll be finding an integrating factor, or it's separable. So it's one of those methods. So you're always going to have a choice to pick which one you're applying. So they're not going to be exact or homogeneous. Okay, so having said that, so what kind of problem are we going to do? We're going to do tank problem. Tank, or you can call it salt, right? Because we're going to be measuring some salt in a tank. Problem with initial value. So that's one type of application. And then the second type of application we're going to do is going to be compound interest. So these are the two types of scenario that we're going to work with. There's also an application called Newton's law of cooling. That's also in the textbook, but that's not required for this course. So you can ignore that section, that tiny subsection, if you're reading the textbook, okay? We're going to only do the salt and the tank, and we'll do compound interest. So these two applications we're going to work with. So here's the scenario, okay? So let's start with application 1. We're going to do tank problem. So let me give you a drawing. So I'm not really a great artist. I can't draw well, but I'm going to try to draw a tank. So suppose you have a tank, a cylindrical tank. So here's a cylinder. So the shape of the tank is irrelevant. It doesn't matter. So hopefully this looks like a cylinder, but again, I'm not a great artist, but I can draw a little. So suppose you have a tank and you have a liquid coming in and you have liquid exiting the tank, right? So I should really erase this part. So here we have a portion that allows the liquid to exit, and we have a liquid coming in. So let's suppose we have liquid coming in and we have liquid going out. And suppose initially it has some liquid. Okay, I can't really draw liquid, but good enough, right? Okay. All right, so that's the scenario. You have mixture in, right? So the liquid that we're pouring inside the tank, it might have some concentration, right? So, or it might not. It could be just pure liquid coming in. So mixture in, and then scenario of mixture out. Okay. So think of something like this. So we have a tank with water. It could be pure or it could be impure, okay? That's already in the tank. And there is more water coming into the tank, and there is also more water exiting the tank. What do we want to measure? Well, we want to measure the amount of salt in the tank. That's what we want to do. Okay, so that's the goal. So let me write down the goal for us. So our goal is we want to measure or you can say keep track of the amount of salt that is inside the tank. So that's what we want to measure. So have this scenario and think of, we want to measure the amount of salt in the tank. So we're going to introduce some variables and we're going to write down what do they represent. Okay, so here are some terminology. And units. Unit is important, so let's keep that in mind as well. And notation, what the variables represent. That's also important for us. So first we want to introduce the variable Q. Okay, so Q of T, that's going to be the amount of salt. So Q will represent the amount of salt at any given time, little t. Okay, so you can see that the little t will represent time. And then we want to use C of t. Well, C of t is the concentration. Okay, so that's the concentration function. Well, how do you find concentration of something? Concentration is always an amount over volume, right? So this is a formula you want to remember. So is the amount. So because we're measuring salt, amount of salt over volume. Okay, think of it as C of t is given by the formula Q of t, because that represent amount, and V, I'm going to use that for volume, so let's call it V of t. Okay, so just giving you more formulas. And then another thing you want to keep in mind is notation. So units for these notations. So units for concentration. What are some common units for concentration? So if it's amount over volume, your amount can be measured in gallon, right? Sorry, not gallon, grams. Volume is gallon. So you can say grams per gallon, or your amount could be in pound. So pounds per, could be liter, right? That's another way to measure volume, and so on. So that's common notation for units for concentration. And then we should also know the units for amount. So that's, I already mentioned, it could be in grams, kilograms, or it could be in pounds. Okay, and then volume, so units for volume, that could be measured in gallon, right? Or we can use liters, and so on. And time, we're going to be using a little t, and that could be in minutes or seconds, right? So hour, so on, right? So these are the units that we want to keep in mind. Now, how do we bring in derivatives into this? Well, if you go back and start thinking about the scenario, we have mixture coming in, we have mixture coming out. So there is a rate of change, right? Rate of change in this such scenario. So we're going to introduce the change in the amount of salt. So that's going to be dq dt. Well, what is that going to represent? Well, that's the rate, right? Derivative is the first derivative is always the rate. So it's the rate of how fast. So right. So Andrew, I will scroll up. So let me know if this is good enough. Okay. So so the first derivative is the rate, right? So it's the rate of how fast the amount of salt changing at given time. Okay. So all right. So you're good. So dq dt is the rate of how fast the amount of salt changing per given time. Okay, so that's the derivative. Well, how do we measure this change? Well, it's definitely going to depend on how much coming in and how much coming out, right? So we're going to say, okay, so dq dt, it's going to depend on big R coming in, right? And big R coming out. So now, how do we measure rate coming in? Well, it's going to be measured by how much water coming in and how much concentration coming along, right? And then same thing as how much going out and how much concentration going out. So I can rewrite the big R with this notation. So we can say rate in and then concentration in. And rate out is going to depend on how much liquid exiting. So we can say rate out times concentration out. So these are the words to measure big R and in and out. So I'm going to simplify this. So we have some rate coming in, little r in, and then we have some concentration coming in, okay, Cn, minus r out. I'm going to say little r out times concentration out, so C out. So we sort of simplify the formula a little bit more. So how much coming in, rate, and concentration, it will always be given to you in the scenario. How much going out, that's also going to be given to you in the formula, in the scenario. But what about concentration out? How do we measure that? Well, if you think about it, concentration, we said it's going to be measured by the amount over volume. So that's the formula we're going to use for concentration out. So I'm going to modify this formula just a little bit more. We're going to replace concentration out with the following. So we have dq dt is equal to R in, concentration in, minus R out. Concentration out, that's going to be Q of T over V of T. Now let's think about it. How is the volume changing in the tank, right? If you think about it, you have rate in, rate out. So that's affecting your volume as a linear function, okay? So we can rewrite that. So V of T is a linear function. So that means I can modify V of T to be some initial volume, right? Plus the slope. Well, the slope will depend on the rate coming in, rate going out. So that's going to be R in minus R out, and it will vary along with time. So that's going to be replacing V of T. So to sum this up, we have dq dt, which is going to be measured by R in, C in minus R out, and C out, that's going to be modified with Q of T over V of T. Well, V of T is a linear function, so we have V initial plus R in minus R out, that's the slope, times T. It's a function of T. So let me just write this here. V0 is the initial volume. So that's the magical formula that we're going to use to measure the amount of salt in the tank. Okay, so this is something you have to remember. Along with the initial condition. So what is the initial condition? Well, that's going to be Q of 0, right? So Q of 0 is the initial amount of salt. So it's the initial salt amount. Okay, so that will be the initial condition. So this represents the modeling for first order. Now here's something to keep in mind. What kind of equation is this? So if you think about it, this sort of looks like a linear equation, right? So if you move the last term, R out Q of T over V initial V of T, right? If you move this to the left side, it becomes a linear equation. Now what if your rate in is 0, or initially you have no concentration, you just have pure water coming in? What kind of equation does it become?
Separable.
Exactly. So if you think about it, so here's something to keep in mind so you don't struggle with it when you're solving this equation. So so let me just write that as a remark. So if you so here's a remark. So if you happen to have C in, concentration in, or rate in is 0, right? If any of these are 0, then the equation above, so when I say equation above, I mean the box, okay? So this one is separable. Otherwise, use the method of integrating factor. Okay, so that's something to keep in mind. If fresh water is coming in, that means concentration is 0 because there's no salt coming along with the water. So you'll make solving a bit easier. Okay, so that's the scenario, and here we have the formula with the initial condition. Any questions? Okay, so for next few minutes, I'm gonna start writing down a problem that we can work on, and then I'll let you guys start your quiz at 7:38. So here's the first problem that we're gonna start with. So let me write down the question for you because I didn't type them. So initially, a tank with capacity of 150 gallon contains 330 pounds salt. This salt in 100 gallon of water. Okay. Assume that the mixture, the water containing 1 pound per 1 pound of salt, so per gallon, is entering the tank at a rate of 3 gallon per minute. Okay. And the well-stirred mixture is draining from the tank at a rate of 2 gallon per minute. Okay, so you should have an idea where this is going, right? You should write down what's given to you. And now here's the question part. So A, find the amount of salt. So that means you're looking for Q of T, right? Because that's the amount of salt in the tank at any time T. So no, yeah. Thanks, Andrew. Okay, so that's the first part. And the second part, we want to know, find the time, little t, when the tank is full. Okay, so here's a typical question you might see for this section. The first thing I like to do is just write down what's given to me in the problem and then figure out what is it asking us to find, okay? So I'm going to go ahead and highlight what's been given to us. So initially a tank with capacity of 150 gallon, 50 pound of salt, dissolve in 100 gallon of water. Assume that the water containing 1 pound of salt per gallon is entering the tank at a rate. So this is important, right? And Worcester mixture is draining, so that's important, at a rate of this gallon per minute. So I kind of highlighted the important components for this problem. So now you guys tell me what's given. Someone, if you want to speak through your audio, please do that. So let's write down what's given to us. What does 150 gallon represents?
VO.
Hold on. Right, the tank, right? So the capacity is 150. That means that's how much it can hold, right? So that's not really VO because VO would be the initial amount in the tank. So capacity is in general how much this tank can hold, and then it's going to start to overflow, okay? So I'm going to hold on to 150 because that's not VO. Now, what about that 30 pound of salt? What does that represent?
Isn't that the initial value that's already in the tank? So would that be
So
VO?
no, the initial amount is Q0, right?
Oh yeah, sorry.
Because when time is 0, right? That's weird to say when time is 0, but I hope you guys know what that means. When you're starting, right? The starting point, you already start with 30 pound of salt that's already dissolved in the water. Okay, so it's already sitting there when we just started this process. So that 30 pounds of salt is our initial amount. So initially we have 30. Okay, I'm going to ignore the units, but hopefully that makes sense. Pounds, right? Q is always in pounds. It's dissolved in 100 gallon of water. So what does that 100 gallon represent?
V of 0?
Yep. So that's V sub 0, right? So VO or V naught, I think that's the reading of this. So that's 100 gallon. And then assume that the water contains 1 pound of salt per gallon, entering the tank at a rate of this much. So what is our rate in? What is our concentration in? What are those components? So concentration is always the amount over gallon, right? Volume. So concentration in is 1. And rate in is 3. Hopefully that makes sense. And it's well stirred and the mixture is draining. So we have R out, which is 2 gallon per minute, and C out, that's going to be a function, right? We have to figure out what that is. C out is going to be Q of T over V of T. So what is Q of T? Well, we don't know. We're looking for it. Well, V of T is the linear function, so it's the initial amount plus rate in minus rate out times T, which will modify to this formula. Q of T is going to be initial volume, which is 100, plus, so rate in is 3, rate out is 2, so that's 3 minus 2, that's 1, times T. That's our C out. I'm going to set up the question next time, but you can also set it up for homework if you want to, and we can talk about it next time. Any questions up to this point? So we have everything set up and we'll continue rest tomorrow. Let me know if you guys have any questions. Okay. So the quiz is 20 minutes. So now I need everyone. So I don't know if you guys can see the quiz yet, but I just need everyone to just relax. So we just had this session. It was pretty 1 hour, 40-minute session, pretty long. So just relax and take a deep breath, and then you can start your quiz. But keep in mind, I'm going to be here, but I'm going to mute my audio and video. And you should only, if you have any questions, don't write on chat to everyone. You're only going to write chat to moderator, meaning that's me. Okay, so you cannot write chat to everyone, just write chat to me if you have any questions. If you don't have any questions, just finish the quiz and you're good to go. Okay, does that make sense? So the quiz is on Blackboard, right? Just keep in mind, don't chat with everyone. You can only chat with the moderator, which means me, just in case you have questions. So have the session on just in case you have any question, but you can mute your audio and video is already muted, but just mute your audio and I'm going to mute mine as well.
Professor?
Mm-hmm.
Where is the quiz exactly on Blackboard? Like, where do I click?
All right, so if you go back to this page, and on the left side, there's a component that says course materials.
Oh, okay.
Yeah, do you see the
Okay.
quiz?
I don't see anything.
I don't see anything.
Yeah, so
no.
maybe another minute or two. It should pop up right over there.
All right.
Or just refresh the page, right? All right, so yeah, that's our lesson for today. So we'll continue tomorrow, and all of you good luck with the quiz.